Okay, so like I was saying, this last time we expanded the first principle of thermodynamics to a new type of system that we call open system or control volume systems, okay, in which this time the mass is not still within the system, but the mass is flowing, okay? So we needed to rewrite everything in function of time. So we started doing this problem where I think the substance is water because it was steam, okay? So the steam going inside a turbine and it's gonna come out through two different little exits, okay? So I think the question was to find what is the velocity of the flow at each one of these inlets and two exits, okay? So we started working on it. We found the mass flow 1. Now that we have the mass flow 1, we derive the equation that the velocity at 2 will be n2 v2 divided by a2, where the area we assumed it was a circular cross-section. So I think the only thing that is left over here is to do the calculation, okay? All right, so let me take a new page. One more person. Admit. Thank you. All right, so this should be page 64. I can move this instead of me moving the page. There we go. So lecture 13. Okay, so what we are doing is the continuation of problem 419. Okay? Alright, so what we need to do here is a numerical application. So velocity, so numerical application, the velocity 2 will be equal to what? N2 we found to be equal to, have it here, right on top, 21.022, and that's kilograms per second. Okay, so let's keep that in mind. So that's correct units. V2 over here is calculated is equal to 0.04739, and this should be cubic meters per kilogram, okay? And this is kilogram per second, okay? So that the kilograms cancel out. And at the bottom, we're gonna have the, okay, we didn't calculate it, but the pi over 4. And let's see, what was the diameter at 2 is 0.25 meters. So times 0.25 square. And this, well, go ahead and do the calculation, but to save some time before the class, what did I do? I think I went here to see the solution, not to waste any time. But if you want to check, guys, so this should be equal to, so we are close to this value, 21.02. This is the same one, this is 25, so it gives about 20.3. Okay, but go ahead and check if you want. So this should be 20.3 meter seconds. Okay. So now we need to do something similar, but at the exit 3. Okay, so now what do we know about the exit 3? Is that if they give us here the quality, that means that at exit 3 the state of the water is a mixture. Okay, so let's say state 3. So not state 3, sorry, at point 3, or at exit 3 at point 3. we know that it's a mixture because they give us x3 equal to 0.9, which is the same thing as saying that is 90%. Okay, so remember we need to know two things. So what do we know here? We know the quality and we know what is the pressure. Okay, so let's say, so we need to go to table what? So I think this should be table A3. Let's go back. I think I opened the tables here. So table A3, liquid vapor pressure table, or yeah, it looks like it's going to be table A3, but this is English units. All right, so we go here, table, this is temperature here on the left. We go here to pressure, and what is the pressure we're dealing with? I think was 0.7 bars. Okay, so at P equal 0.7 bars. All right, so go back here to the table. So do we have 0.7? 0.7 is right over here. Okay, so in order to calculate V3, what do we need to know? We need to know VG and VF, no? So remember last time there was an issue. What does the 10 multiplied by 3 means? It means that this value here has already been multiplied by 10 to the 3. And I think I told you that a way to know that is what? When is the water going to occupy more volume or more space? When is it on the liquid state, the fluid state, or the gas state? When it's in the gas state, no? So if you multiply this one by 1,000, it's going to be much bigger than this one. So it would make no sense, no? So what does that mean is that they did multiply this one already by 1,000. Okay? So if you want, on the page, right over here at P equals 0.7, you're going to have V fluid is equal to 1.0360 10 to the minus 3. And the gas is 2.365. All right. All right, so now that we know this, we can say then that V3, specific volume fluid, will be equal to what? Will be equal to V fluid plus X3 Vg minus V fluid. Okay? All right, so this will be equal to what? This equation you should have get it. Remember, I told you that in class you can come and let's see, what is that page? I told you to bring to class this one over here, no? So I'll tell you, always bring this page with you if you can, the same one with the units, okay? So let's go back over here. So we do this calculation. This would be equal to what? 1.036 10 to the minus 3 plus 0.9 times 2.365 minus 1.036 10 to the minus 3. So if you want, go and check the value, but today I decided just to look over here at the solution, but check the values. 0.36, this should give you 2.1286. So 2.1286. And this should be cubic meters per kilogram. Okay, so using the same relation as before, what is the definition of the mass flow? Definition of the mass flow is the volumetric flow rate, so AV3 divided by the specific volume. Okay, or this would just be A3 V3 divided by specific volume. So this is exactly as before, so solving for the velocity, we're going to have that V3 will be equal to what? Will be equal to the mass flow rate at 3 times the specific volume divided by the area at 3. And this should be equal to the same thing on top. And the area here should be what? Pi over 4 d3 squared. Okay, so we have over here d3, m3, so we have d3 is known. Check. The mass flow at 3, I think we found it earlier. In this page, we found that M3 dot is equal to 84.09. Okay, and D3 is equal to, from the problem statement, we have here that is equal to 1.5 meters. So 1.5. So we go and do the numerical calculation. We're going to get what? V3 should be equal to 84.09 times V3 is equal to 2.1286 divided by pi over 4, and the diameter is 1.5 square. And this should give you, let's do again our little cheating here to save some time, that this should be, so 84.1 is almost the same, 2.1286 divided by pi over 4, 1.2, so approximately 101.3 meters per second. Okay, and I think that's all we needed to do, no? Okay, so let's see. Okay, I did hear you, so you say about V1, no? Okay, so let's see if we can find V1. Let's see if there's a way to find V1. At point 1, I'm looking at, they don't give you the size of the inlet, no? So, now I don't think there's a way to find V1 here, because you don't have the size of the pipe, no? So let's see, I didn't see here on the solution here, but let's see if they did at the beginning. V1. Now, it doesn't look like this here either, okay? All right, so let's go and do more problems of this type, because this is really the type of problems we'll be solving from now on. Also some of the other ones, but these ones become now more dominant. So 61, 60, and 65. Okay, so I'm going to pause for a second. I'm going to go look for another problem. Alright guys, so let's do the problem 451. So just do the figure for now, and then we see if we need to add something to the figure. But basically, again, it's a turbine, so with two exits. But it has more involved than before, okay? Because you see there's a heat transfer and there is work, no? All right, so let's see what will happen here. So we have our turbine. All right, that's connected to a shaft. This is generally the case. On the engines, the turbine is connected to a shaft that runs the compressor at the front, no? We have here 1, 2, exit 3. So let's see. It's coming in through 1, the same as before. It's leaving 2 and 3. So we know P1 is 1800 psi and T1 is 1100 Fahrenheit. They give you M2 to be equal to 0.2 M1. Okay, so it should be here. M1, M3. P2 is equal to 600 and T2 equal to 500. Now at 3 we know that it's saturated vapor. So remember, that's important because that tells you one thing, no? And P3 is the other thing that you will need to go to the tables, is 1 psi. And there is work done by the turbine, this is always the case. And there is heat transfer coming out of the turbine. All right, so the work of the turbine is how much? Let's read the product statement. So steam at 1800 and 1100 enter the turbine. The internal mass flow is extracted, 20% of the internal mass flow is extracted at 600 and 500. Okay, so the rest of the steam exits saturated vapor at 1 point, okay? The turbine develops a power output of 6.8 10 to the 6 BTU hours. So the power, so the WT on the figure is 6.8 10 to the 6 BTU hours. Okay. Heat transfer from the turbine to the surrounding occurs at a rate of 5 10 to the 4th BTU hour. Okay, so neglecting kinetic and potential energy effects determine the mass flow rate of the steam entering the turbine in pounds per second. Is something else at the top? No. Okay, so we look at the figure I did. This is my figure. So I'll put these values over here. If you want, you can add here neglecting kinetic and potential energy. And what we need to find is okay. So here, the stuff I'm looking on the exams is that you understand the material. I'm not looking for the final result. So every time we apply, let's say it's a closed system or open system, you need to define what is the system, correct? Okay, so what is the system here? The system is the turbine. Okay, so this is our system. So for the system, what do we know? We're going to have conservation of mass. which means what? They didn't say steady state, but I'm sure it's steady state. Is that the amount of mass coming inside the system needs to be equal to the amount of mass leaving the system, no? Okay, so in this case, what do we know? M2 is given to us is equal to 0.2, so it's 20% of M1. So consequently, what's going to be M3? 0.8, 80% of the mass flow 1, no? Okay, next we can write applying first principle to above control volume. So if you want, Johnny, instead of calling this system, Johnny, I'll call it control volume, might be more specific. So this is your control volume. So what is the Johnny equation that we derived the other day? It will be Q dot minus, so heat transfer minus power. So you want this, let's look at it this way, all right? You put these two values, and now this is your control volume. All right? So what is coming in inside the volume? This is just the way I do it. The mass coming in will be M1 at a certain pressure, but it will bring also some internal energy. And what is internal energy plus work done by the pressure? We say that is enthalpy, no? So we can say this is M dot 1 H1. And now, is it anything else coming in? As the flow, this is the only one, no? Now, what is coming out of the system? We have M dot 2 H2 plus M dot 3 H3. Okay, what is coming in, I put it on this side, what is coming out, I put it on this side. And this one, you could do the same thing with this one, but then you need to be careful with the sign, okay? So this is generally the way I like to do. So here, you can see right away that you know that M2 is 0.2 M1, the mass flow 1, and that M3 is 0.8, the mass flow of 1. So we can rewrite this equation as Q dot minus power plus M dot H1 equal to 0.2 M dot 1 H2 plus 0.8 M dot 1 H3. Okay, if you want, let's do some algebra. Instead of doing it once, it should be equal to Q dot minus power. Now let's say we factor by M dot. I'm going to start by this one. We're going to have 0.2 H2 plus 0.8 H3 minus H1. So now we need to solve for the mass flow 1. So we just solve. From the previous equation, we solved that the mass flow 1 should be equal to what? Q dot minus power will be equal to 0.2 H2 plus 0.8 H3 minus H1. So you see, if you do this on the exam, on the problem, you show me that you understand the material. So just by writing this, probably you get about 7 points out of 10. Okay? Because now the rest is to know how to use the tables, no? And to do a numerical application. So in this equation, we know Q dot is given to us. The work is the one of the turbine is given to us. So what do we need to find? We need to find H1, H2, and H3. Okay? So let's first find H1. So let's see. Remember, in order to use the tables, we need to know, this is the previous problem. Okay, this is the new problem. We need to know two things, no? Do we know two things at point 1? We know the pressure and the temperature. Okay? So let's say we can go, so let's say we don't know which table yet, but let's say table A something E at what? At P1 equal 1800 and T1 equal 1100. All right, so let's find out what is the state of the water at that point. So let's go to the table. So this time we need English units. Here we go. So it's down. So we could go to, let's see, we have the 1100 here, or we can go to the pressure. I think the pressure will be easier. Generally, the pressures are easier to understand. So pressure here, 1800. Okay, if the saturation temperature at 1800 is 621, Fahrenheit, no? 1800, and what is the one we have over here? Is 1100. So what is the state of the water at state 1? What is it? It should be superheated, no? Vapor or gas. So basically we can come here, that this is table, I guess is A3E, all right? Yeah, so from table A3E, okay, you find that T saturation is equal to 621.21, which is lower than 21, so this will be so basically what I'm saying is that this will be, since T1, this is lower than T1, this means we are on the right hand side of the curve, no? So we are on the steam. Did I close that figure already? Yeah, already closed it off. Okay, so that means that we need to go to which tables? We need to go to the tables of superheated, no? Which are the table A4. So table A4, superheated, means we are on the right side of the curve, no? So now we need to look at 1800. So hopefully it's going to go to 1800. We won't have to interpolate. All right, probably go faster than this. Okay, 1600, that's good. 1800, and the temperature is 1100. Okay, so we need to find the H value. So this is V, generally this is U, this column is H, and this one is S. Okay, but we haven't started still the S. But let's go up to see what is the third column is enthalpy in BTU per pound. So that means that we go to 1800. 1100, and we get H1 should be equal to 1542.5. So then we go to table A4E at P equal 1800 and T equal 1100, and we get that H1 is equal to 1542.5 BTU per pound. Okay, now we need to find H2. Again, we know two things about H2. We know the pressure, we know the temperature, no? Okay, so what can we do? So we say at state 2, we know that at P2 equal to 600 and T2 equal to 500. Let's see what would be the state. So we can go again to table, I guess, A3E. We can almost get it from here as well, but let's go table A3E. I think it's always the easiest. So A3E at 600. What is the saturation temperature? 486, no? So again, what does that mean about the state of the water at the exit 2? It will be superheated, no? But this time not for a lot. Okay? So table A3E. I mean, following the same as before, T saturation is 600, 486.33, lower than T2. So basically this is gas, vapor, or superheated. We go to table A4E at P equals 600 and T equals 500. I'll show you what I've been writing. So basically, table A3E at P2 equals 600, T2 equals 500. We find that T saturation is 46.33, which is lower than T2, no, because it's 500. So we know it's superheated, gas vapor. So now we need to go to table A4E at 600 and 500. So basically the same process as before. So 600. 600 and 500. The value for H2 will be 1,216.2, no? All right. So we go table A4E, we get that H2 is 1,216.2 BTU LB. Okay, and finally for H3, what do we know H3? They're already telling us that it's saturated vapor. Okay? So if it is saturated vapor, what it means that H3 is going to be equal to H gas at what pressure? You need to know two things. So you know the first thing is that it's saturated vapor. The second thing you know is that it is 1 psi. Okay? So over here, the best thing probably is to table A3E. You could get it also from table A4E, but let's do it at this. So at P3 equal 1, H3 will be equal to H gas. That will be equal to, we're going to find out. So let's see, what's the pressure? 1. You could get it from here as well, okay? Table A4E, let's see if I have 1. I'll be surprised. I mean, this computer is extremely slow. I'll be surprised I have 1 here, 21. What should be the value? Saturation should be 1,105.8, no? Okay, from this table. But let's say we table from table A3E, what is the pressure? 1. So let's see. 1 here, we should get Hg, which is exactly the same thing, no? 1000, if I highlight it, is 1105.8. Okay, so you can see you could get it from either table. So H3 would be 1105.8 BTULB. Alright, so I want to go to the next page. So substituting into the expression we had before, dot 1, the mass flow equal to heat transfer minus power of 0.2 H2 plus 0.8 H3 minus H1. So the incoming heat transfer from the Poisson statement was equal to what? To 5 10 to the 4 and the power 6.8 10 to the 6. We didn't do any mistake. Alright, so I will just substitute now. What we're going to get is m dot 1 equal to, so let's see, 5 10 to the 4 minus 6.8 10 to the 6 so here let's be careful for 1 second. Remember the sign convention, if the heat is coming out over here, what is that, positive or negative? This should be negative, no? Heat going in is positive, heat going out. So maybe you should put here a negative sign. And now, work done by the system is positive, okay? On the textbook sign convention. So we should have then, both of these two should be negative. Okay? Looks like. So hopefully we just have to take the magnitude, or maybe this is going to become negative. We'll find out. So it should be equal to what? Divided of 0.2 H2 we found to be equal to 1216.2 plus 0.8 times H3, which is 1105.8 minus H1, which is 1542.5. Okay, so if you want to do the calculation, otherwise I'm going to do my little cheating here. Why is this so slow? But do the calculation, what you get. I think the bandwidth is giving up. All right. Don't think that I'm not scrolling down the mouse, but you see, maybe too much. Yes. It's like when I do something, it's reacting like 5 seconds later. This is 51, no? I think it's just faster for you to do the calculation. Okay, anyway, let's go look at this. Let's see what I have for the H and so on. Let's see what I have on the values. Okay, basically the same thing we did now. You see the equation. So both of them are negative. We have 100, 2016.2, 105. I remember that one. 1542. So this should give you, oh, be careful here because this is BTU per hour. Oh yeah, okay, so we need to be careful with this. So I did not pay attention. So the units, okay, so units for these ones here are BTU hours. Okay? And they want us to give it per second. So what you need to do is transform the hours into seconds. Okay, so let's do that. Otherwise, we're going to have to do the calculation 4.59. So let's see. So they want the result in seconds. And because this is BTU hour, we need to transform so 1 hour should be 3,600 seconds. And this will give you 4.59. £4.59 per second. Okay, so expect a homework about this, no? All right, we have, what, half an hour? I don't want to start the new chapter because it's a lot of new stuff, so let's see if we find a different problem. Maybe we won't finish it, but at least we can start it. I'm not that sure is the because look at when I do this and this is on the computer. I don't know, maybe it is. Okay, so 444. Let me go to 5 and we'll go back. Might be easier. So up. So this is really the one in function of time. Maybe next time I'll do this one, or one of these ones where it's, the other type of one you can have is these ones here. These are good, huh? So 4107, let's see this one less complicated. Let's first do this one. Let's see this one. Let's see if we can do one with a valve, a little bit easier. I don't think we covered the valve. This stuff is complicated, but it's no more complicated than we just did, okay? Let's see if you see one with a valve. All right, let's do first this one. Is that okay? Just like that. 498. Okay, completely randomly, just because I see the valve. I just want to mention something about the valve. So just do the figure. So basically on this one, you have saturated refrigerant So saturated R134A, which is the one, Johnny, you have in your car, at a state of T3, 115 degrees Fahrenheit, and the mass flow at 3 is 1.5 pound per second. Okay? And this is state 3. So it's not state, it's point 3. This goes through a valve. So it's a throttling valve, which basically means a throttling device. And you go to 4. Where you know at 4, P4 is equal to 60 psi. Now this is going to go into an evaporator or a condenser. Okay, to state 5, where you know at 5 is saturated vapor, P5 equal P4. Okay, it's a heat exchanger, but the heat exchanger is basically a condenser or an evaporator. And then some of in lives at 2 to the bottom of the heat exchanger at T2 equal 528 degree Rangans. Okay, on top of that, there is a fan. I don't know why they did it with the shape of a turbine, but it's fine. There's a fan that I'm guessing when they do the minus 0.2 means that it requires, obviously a fan requires power to function, no? And that power is equal to 0.2 horsepower. And that inside this stuff here, there is air. So be careful here because look, there is two different substances. On one, there is air. So on one side is refrigerant 134. On the other one is air. So this is like a simplified version of the AC of a car, no? A very simplified one. And you know that T1 is equal to 535 degree Rangans, and the specific heat of the air is 0.24 BTU LB Rangans. Allow space to put the units. So be careful because over here, what substance is coming out of here at T2? Is it air or refrigerant? This should be air, no? You have the fan, this is going to go through this, it should be air. So at T2, make sure to specify that it's air. I want to show you for a second the figure I've done. I mean, it's that one. This is the figure I've done, okay? Okay, so since you have the figure, really the only reason why I'm doing this, that I want you just to memorize this, because the derivation is so simple that it's useless, is that whenever you have a valve, okay, what does a valve mean? Is that you're not going to lose any energy. Here you agree that when you open a valve, the fluid is not going to go, I mean, you're not adding anything to it, no? Okay, so what's going to happen here is that you can say that H4 is going to be equal to H3. So this is the important part, and this is due to the valve. Okay, that's the valve that implies this stuff. H4 equal H3. Okay, so the rest should be pretty similar to what we have done. Let's see what we need to find in this problem. So 498 Okay? So figure 498 shows three components of an air conditioning system. Refrigerant 134 flows through a throttling valve and a heat exchanger, while air flows through a fan and the same heat exchanger. Data for steady states, so it means that you have conservation of the mass, no? Steady state. Operation are given on the figure. There is no significant heat transfer between any of the components and the surrounding. Perfect. Kinetic and potential energy effects are negligible. Modeling air as an ideal gas with constant Cp equals 0.24 BTU LB Rankines. Determine the mass flow rate of the air in LB seconds. Okay. So, okay, let me hold on 1 second, please. Okay, so over here, I'm not 100% sure now how to get to the answer, but we get to the answers. Like I tell you all the time, you don't have to be scared to get into the dark tunnel, no? As you move in, you will start seeing the light, but you need to start right at the beginning. So let's say I'm going to select as control volume this one over here, initially. Okay? And this is important that you specify which control volume, because if you don't tell me which control volume you are considering, here how many control volumes you could take. You could take just the valve, you could take just the fan, okay? Or you could just take the heat exchanger as we are doing. So for control volume 1, the first principle of thermodynamics is what? So let's say the general pressure will be Q minus work. Okay, now what is coming into this one? You do this one. There is air coming in through the fan, no? You can say with this sound plus m dot 1, so m dot air h1 and this is what we need to find, no? The mass flow of air. Anything else coming inside this one heat exchanger will be the refrigerant 134 at 0.4, no? So plus M, let's say refrigerant, I'm just going to call it R for refrigerant, H4, so this is coming in. Now, what else is coming out? I think it's the way they did it. Okay, also on the solution. And now that I see the equation, I think we're going to get the same terms. So now, what is coming out of this system? We have at 0.2 and 0.5, no? So at 0.2, we're going to have mass flow of which substance? Air, H2, and then at 0.5, we're going to have plus M refrigerant of H5. So now, this is why the figures are important. In here they give power, but be careful. For this control volume here, is there any heat going in or out? No, you don't see it on the figure, it's not on the equation, so this is 0. Is there any power going inside in this control volume? No, so it should be 0. Everything comes from the figure, no? So from here we can rewrite what? We can write that, so be careful here, I might go a little bit, I'm going to write something that Might be not 100% clear, but I hope it's going to be. So let's factor out on one side the one of the refrigerant. So let's say we move the refrigerant to the right. So we'll have what? M refrigerant, H5 minus H4. I move them to the other side. I'm going to move the ones of the air to the left-hand side. So we'll have what? H1 minus H2. Okay? But now, what do they say about the air? We can say that it's an ideal substance. But what is something specific about the air? And that this substance is defined as what? A substance that does not change its state. If it does not change its state, what is the assumption we can do? Is that this term over here will be basically equivalent to what? Cp T1 over T2, no? So this is the part that they say to use the ideal gas relation. So they give you T1 and they give you T2 actually. So I don't know why they give you the power of the fan. I don't think it's used for anything, but anyway. Alright, so now from this equation we can say that the mass flow of the air should be equal to what? Mass flow of the refrigerant, so H5 minus H4 divided by Cp T1 minus T2. So in this problem, do we know the mass flow of the refrigerant? I mean, if they give us M3, we know M3 is going to be equal to M4 is going to be equal to M5, no? Yeah? This is the air is going through the same pipe, no? Yeah? So we can say that the mass flow of the refrigerant is really going to be equal to M3. Right? So let's say this will be 1.5 lb second. So M refrigerant will be M3, 1.5 pounds per second. So that's good. We have this value. What else do we know from that equation? Cp is 0.24. I don't have the units, but I think it's BTU per LB Rankins. Let's go and double check. Is 0.24 BTU divided by LB Rankin. All right. Okay. Do we know T1? T1 is given to be 535. All right. T2 is 528. So really, what are the two things we need to find? H4 and H5. Okay? So let us find H4. So do we know two things for H4? Sorry for that. Let's see what that is. Okay, so we need to find H4 and H5. Okay, what do we know about H4 and H5? We know that this should be equal, no? Yeah? So, alright, so let's go find the tables for the refrigerant. So in English units, let me save some time to see what is the number of the table. Where we go faster. Why do they have the work here? Let's go back to the, let's see what is happening here. H4 equal H3. So table A10E. Now this is for H3, would be H4 equal H3, which we say that we had. Table A10E. Okay. So table A10E, that will save some time. Touch down. A10E. Nine. So at A10E, what do we know? The temperature is, how much was the temperature? 1. So table A for table A10E at T equal 115 Fahrenheit. So here's the Fahrenheit. We have that H will be H fluid, because what is the pressure that we have is 60, so it's lower than 149.63, so we know it's going to be liquid. So the H3 should be equal to H, so H3 or H4 equal to H3 equal to H fluid at 115, and that one is equal to 49.63. No, yeah, 49.63. BTU LB. Okay, now the next thing we need to find is H5, which is the one over here. So what do we know about H5? We know that it's saturated vapor. Okay, so at point 4 we know, so for H5 we know that it's saturated vapor. We know two things, saturated vapor. And what else we know? P5 equal P4 is equal to 60. Alright, so probably we need to go, I guess, to table A11. Completely guessing here. Table A11. We need to see this one with pressure. So here we have the pressure. We know 60, no? It's at 60. So H4, if it's saturated vapor, means that H5 is going to be equal to H gas, which should be 108.72. So from table A11E at P equals 60, H5 equal to H gas equal to 108.72 BTU LB. Okay, so now basically we have all the information that is needed in order to find the mass flow of air. Okay, so substituting, we're gonna have mass flow of air. Oh, we have 2 minutes, so will be equal to what? So let's go right away. Will be 1.5. Let's be careful with the units. 1.5 times 108.72 minus 49.63. So we agree with the units. At the bottom will be CP, we agree as well, will be 0.24 times T1, which is 535 minus 528. So whatever you do, the units here will cancel out and you end up with LB per second. So what do you get if you do this calculation? 32.8? 52. 52.8? Okay, so 52.8. Okay? Alright, so we stop over here. And I will assign a homework for this. This is a matter of practice, like everything else. Stop recording.